Hi, I'm Juha and I'm a hockey player here at USC. I will be going through some physics concepts and examples with you this semester. And remember, just like on the ice, there's no such thing as luck in physics. Just keep your head up and work hard. In this video we'll review Newton's laws, all three of them, that form the basis of all classical mechanics. Without further ado, here's the first one. It says, a body acted on by no net force moves at constant velocity, which may be zero, and zero acceleration. In other words, what they are saying, or Newton was saying, that to change velocity of an object, net force is needed. This means that if there are forces acting on the object but they all cancel each other, this is the same as there would be no force at all and the velocity of the object doesn't change. Newton's second law, on the other hand, tells us what happens if there is a net external force acting on the body. In that case, the body accelerates. In other words, if there is a net force, force is a vector, there will be some acceleration A, also the vector. The direction of the acceleration is the same as the direction of the net force. So this is evident from this vector equation, of course. And the magnitude of the acceleration depends on how heavy is the object, that is, the mass. A special case where Newton's second law is applied is circular motion, and that pops up in a lot of problems, so let's have a look at that. So we have this particle going in a circular motion clockwise, like indicated by this arrow. So at this point it has velocity 1, and sometime later the velocity is v2. So the magnitude of the velocity is same in both cases, but the direction has changed. And this is crucial to understand, that when we're talking about change of velocity, velocity is a vector quantity, so it has both direction and magnitude. So when either one of those changes, there will be acceleration. So although this object is moving at constant speed on this trajectory, it has acceleration because the direction of the velocity changes. And in that case, we can write the second law as follows. The net force F equals mass times the radial acceleration. So radial acceleration is always towards the center of the circle, and this is important to remember when solving problems. So like this, a radial always towards the center of the motion. And what is the magnitude of the radial velocity? Or, okay, I'll take this one back a little bit. Let's remove the vector here, because we have to talk about magnitude and direction differently. So the magnitude of the angular, or the acceleration in this case, is in fact v squared over r, where r is the radius of the circle. So in this case we leave the vector notation out because the direction is towards the center of the circle always, and the magnitude comes from this equation, mv squared over r. So that's pretty much the second law that we will be using all of our problems. The third Newton's law says, if body A, for example the foot here, exerts a force on body B, the ball, then the body B exerts a force on body A. And these two forces are of opposite direction, but they have the same magnitude. So basically what is said here is that if there is this force of A on B, this arrow here, there will be equal but opposite force exerted by B on A, the foot in this case. So kicking the football hurts a little bit because the ball exerts the force on the foot. Or when apple is falling towards the ground, in fact the earth is also falling towards the apple. And when you jump off the boat, you push the boat back and the boat pushes you back, and so on. When solving problems using Newton's laws, the division is as follows. So the first law is usually for static problems, when there is no acceleration. There might be velocity, constant velocity, but no change of velocity, hence the name static. And Newton's second law comes into play when we have accelerating bodies, either accelerating linearly or if they are in circular motion, like we saw here. And then the Newton's third law of equal and opposite forces comes into play to help to solve one of these problems if needed. And note that some problems might be combinations of static and dynamic. For example, if we have a box that is pushed on the floor and it's accelerating, so there's acceleration. There's acceleration in the x direction, but no in the y direction. So this is dynamic in the x direction, but static in the y direction. To successfully apply Newton's laws for solving mechanical problems is, of course, just a matter of practice. And we'll look at some of those principles in the example videos.